Okay, guys. Say hello to all of our folks at home. No, really, say hi to all of our folks at home. We miss you. We love you. No, this is being recorded. You guys are, who are we talking to? Okay, guys. So what we're going to do, I mean, you don't need to know this, but I may as well explain it. I'm going to start recording in this class not only the new information, but also the homework grading stuff, so that they can get sort of the full experience. So this is recording as well. So guys, with that said, well, first of all, do you have questions about the homework? No? Then I need to grab do we need a book or can we just talk? Okay, go ahead. All right, we better go look. Question 4. Let's look. You never know. The thing I will mention, though, Matthew, is understand that these questions, these end-of-chapter questions, are good but not always great. They were written by blurry-eyed, starving graduate students. And I know that because I was one of those blurry-eyed, starving graduate students that have done end-of-chapter questions. You make a lot of money. Yeah, like $30 an hour. It was great. But they're not always perfect. So question 4, you're seeing color differences?
Just like in the third one.
Mm-hmm. Mm-hmm. Mine is. Yeah. He's colorblind. Really?
We've downloaded the PDF.
You've downloaded what?
The book, textbook, as a book.
How illegal is that?
It's a PDF online.
Is it from stolentextbooks.com or where did you get it?
It was just that I get a free online PDF. So
I'm guessing that it's not from Prentice Hall.
imagine we did buy it and download it.
In theory, if you had a copy of this book.
Right, theoretically. The third box, the top arrow was just right instead of wrong.
And you're complaining, given that you have a stolen book. So, we probably shouldn't be recording, but okay. So, like, you guys don't even use the physical textbook? But you really, like, when you did your chapter summaries, you did them? Really? Okay, so I feel like Big Brother's watching. Can you email me the link? No, please don't email me the link. No, because we know. Yes. I really, can you get all of your textbooks like this? Yeah, and that said, that's interesting. Well, yeah, I'd love it if you'd send me the email. That'd be great. So guys, other things you want to talk about other than the issues that we're having with bootleg copies of the books? We okay? All right. So guys, let's get this recorded. Then grab something you can take notes with and on, and we'll get going. So I need to get rid of this. And Braden, are you good on this assignment? Matt, how about you? Do we have Donnie on speed dial? No Donnie? Okay. Sophia, you good? Okay. Annika? Ethan, you good? Josh, how about you? Diana, you good? Isaac? Ellie? Landone? Emma? Leslie? Gage, are you good? Ronnie? Kaylee, are you good? And Spencer? Meredith, you good? Okay. All right, so put this away. Grab... Oh, guys, look at that homework assignment. She's a cutie as well. Well, you guys were commenting on how it was nice to have a homework assignment that didn't take a day and a half. Just saying. Hi. We do. No, thank you. You guys are amazing. Thanks, guys. All right, guys. So, as you were titling your notes, nudge, nudge, wink, wink. Guys, as you're titling your notes, I pray, sorry, this is about to get a little New Testament or Old Testament-y. I pray that you're remembering the covenant that we entered into. You will not Google, and especially Wikipedia, anything that we talk about today. And guys, understand it's not because I'm trying to hide anything from you. But guys, the reason is because when we start talking about laws of thermodynamics, these are laws. In the same way that there's a law of gravity. You don't get to argue about it. You just get to try to figure it out. And guys, in the same way that gravity is an idea that is so all-encompassing that there really isn't a portion of our life that it doesn't touch. Guys, thermo's the same way. So when you read about the first law of thermodynamics, when people start writing about this in a scholarly way, there's nothing that's out of bounds. And these become huge conversations. And if you get into the middle of them, you may actually do more damage than good. So my job as a freshman chemistry professor, right, because that's what this is freshman chemistry for you when you get to college. My job is to narrow things down to the point where we understand it at the level that we need to, that we can use it functionally. Okay, so if you're feeling tired and bored over the weekend and you really just want to start digging around on the internet, knock yourself out. But guys, understand the stuff that I'm helping you understand is the stuff you need to know to be able to do this on the test. So, guys, with that said, what we're going to do is we're going to start with a little bit of review. Did you like the little metal block thing? You don't even remember the metal block thing, right? Systems, surroundings, work, falling, kinetic potential energy, total internal energy. We found out that as the block fell, the total internal energy did not change. Remember, as the block fell, we took potential and converted it to kinetic, but the overall energy didn't change. It started at 100. As it fell, it stayed at 100. So kinetic could become potential and back and forth. But then it hit the table, and it lost all of its energy doing work on the air. Remember all of that? Guys, we're going to come back and we're going to use that conversation as a foundation to start to understand this interchange of energy between system and surroundings. Now, guys, this is where there's a possibility that what we're going to talk about is going to contradict what you learned in physics. So let's talk right now. Are any of you doing AP physics right now, or did it last year? Say that again?
I did it last year.
Okay. Anyone else? Or what about this? Most of you have taken general physics. Do you remember anything? Good. Because, guys, here's why. And so, Ronnie, you need to especially understand this right now. So, guys, let's talk about physics for a minute, and then we'll dispel the confusion. So, guys, in physics, you tend to be a passive observer. For example, do you actually remember learning the Doppler effect? Okay, so the idea with the Doppler effect is that you've got a train, and the train is emitting sound waves, or you've got a car that's driving down the freeway at high speeds, and it's emitting sound waves. And if you are the person standing by the train tracks or standing by the road, as this thing goes by, you hear, right? And the sound changes. The reason is because as that thing is coming closer to you, the sound waves are being compressed, shorter wavelength, higher pitch. Then as the car passes you, those same sound waves are being stretched, and that makes the tone go down. Longer wavelength is lower pitch. But then, guys, maybe you learned that interesting idea that not only does this happen to sound, it also happens to light. And you learned about redshift. Did that happen? Let's talk about it for a minute if you didn't, because it's fascinating. Guys, it does not matter what heavenly body we turn our telescopes on. It could be, well, other than in our solar system. But guys, anything that is outside of our solar system, stars and galaxies and everything else. Guys, all of these things that we look at, the colors of light that we see are shifted slightly towards the red. Now, guys, red light is longer wavelength light. So what does that tell us? Go ahead. Everything in the universe is moving away from us. Everything in the universe is moving away from us because all the light that we see is being stretched. We call it red shifting. Now, guys, how could that be if everything that we see in the universe is moving away from us? It all started at the same place. This is some of the best evidence we have for the Big Bang. Because the idea is this. Imagine that the Big Bang happened right there. Okay, so my coffee cup is the center of the singularity. And when this thing banged, if I'm running this way, right, there are going to be things in front of me. How did they get in front of me? They're moving faster. We all started there. So if somebody's in front of me, they're moving faster. That's stretching the light. Now, what if somebody's in this direction? What if Landon's moving that way? Well, clearly he's moving away from me because he's going the other direction. But what if it's something right here? Well, it's moving slower than me. Remember, we all started in the same place. And this thing is moving slower than me, so I'm running away from it. So guys, the only thing that can explain this universal red shifting is that we all started in the same place. You guys know me well enough to know that that does not challenge my faith. But guys, the Big Bang had to happen. Here's the reason we're talking about this. So guys, the reason we're talking about this is the only way for us as a physicist to understand any of this is if we, here's the connection, are not in the system. Think about that. We cannot be in the system as a physicist. Imagine this. Let's go back to the train tracks, right? And the train goes, right? What does it sound like if you're in the train? The same the whole stinking time, right? So guys, the idea is this. To be an effective physicist, you can't be in the system because you're looking at how things around you are behaving. Ronnie, this is where you got to be careful. And for those of you that do remember physics, in chemistry, you can't be in the system. Because, I said that backwards. In chemistry, you have to be in the system. Yeah, so guys, in chemistry, our frame of reference is the system. So you're asking yourself now, why does that matter? Well, guys, let's talk about it. So let's go back to our metal block. Ready? What is the internal energy of this metal block right now? 0, right? Okay. Now what is it? More than nothing, right? Let's call it 100. Did energy go up or down? See the problem? Did energy go up or down? The question is whose? What happened to the energy of the block? Went up by 100. What happened to the energy of me? Went down by 100. Now, guys, in physics, we would call that a negative energy experience because we're in the surroundings. Our frame of reference is the surroundings, and the surroundings lost energy, so that would be negative. In chemistry, we would say that the energy change is positive because we're in the system. It's critical that you understand that difference because, guys, today when we start talking about the first law of thermo, it's all about energy exchange. The tricky bit is the signs. And our signs will always be assigned with the understanding that we are in the system. You get the idea? Okay, so now we get to draw some pretty pictures. And guys, it goes like this. This is a review. If you want to write this down, you're welcome to. But this is where you should be right now. Ready? System. Here it comes. There's your system. Could be a block. Could be sodium hydroxide and hydrochloric acid reacting together. Whatever it is, here's our system. So guys, if this is the system, what's everything else? The surroundings. All of this is a review from last time. So now, guys, let's turn our attention to the system. This system has energy, but there's only two kinds of energy it can have, and what are they? Two kinds of energy, kinetic and potential. But guys, the thing that you've got to understand is that these can interconvert. Kinetic can become potential. Potential can become kinetic. But when they do, there is zero total energy change. Right? Guys, if you're not connecting with that idea, think about our block. 100 joules of energy. What kind? Potential. As this thing falls, its potential energy is going down. Where is the potential energy going? It's becoming kinetic energy as this thing accelerates. So potential is becoming kinetic, but the total energy doesn't change except for air friction. Guys, the total energy doesn't change. If it's 100 joules here of potential, it's 100 joules the whole way down. It's just no longer 100 joules of potential. Some of the potential is becoming kinetic, but it adds up to 100. Right? So guys, potential and kinetic energy can interconvert without changing. So then the question becomes this. If a system cannot change its own energy, then how does the energy of a system change? Let me say that again. If a system's energy if a system cannot change its own energy, then how does the energy of a system change? By interacting with the surroundings. Now, guys, there are only two ways that the system and the surroundings can interact. There's only two ways that these can play with each other. And what are those two ways? Work and heat. That's it, guys. These are the fundamental building blocks that you've got to understand about energy. If we've got a system and we've got a surrounding, guys, the system cannot change its own energy. Kinetic and potential can change all day. But the only way that the energy of the system can change is by interacting with the surroundings with work and heat. And again, guys, we are not dumbing this down because this is an AP class. You've never thought of it that way. But guys, relative to the entire subject, AP is still training wheels. But guys, it's not like you're going to get into your sophomore and junior years in college and they're going to go, guess what? There's more. No, there's not. This is it. There's kinetic, potential, work, and heat. That's it. You guys good? Okay. So guys, with that said, if you want to write these things down, you can. But these are the fundamental rules. Energy within a system can convert from potential to kinetic or vice versa, but internal energy doesn't change. So how does internal energy change? Well, that's number two. Energy can transfer between a system and the surroundings in the form of only work or heat. That's the only way to get energy in or out. You guys good? You feeling okay with the fundamentals? Okay. Then guys, now it is time to define an accounting rule. Guys, if you balance a budget, if you keep track of your spending, if you know how much money you bring in and how much money you spend, guys, the books have got to balance. Well, guys, it turns out that not only do they have to balance financially, they also have to balance in terms of energy. This is called the First Law of Thermodynamics. You promised me that you would not look this up. But guys, ready? This is it. This is the first law of thermodynamics. Simply says this. I would encourage you to write it down. Energy is neither created nor destroyed when transferring between a system and its surroundings. We already know that kinetic and potential can interconvert with no loss. But guys, it turns out that when the system and the surroundings interact, the numbers have to add up. Energy is neither created nor destroyed when changing forms, when changing forms or transferring between a system and its surroundings. Did you guys get it? You're still writing? So guys, if you've written this down word for word, what I'd like to do is I would like to take the previous slide and the information that we had on there, and I'd like to superimpose it on this sentence. So the first thing we need to look at is changing forms. What are the two forms of energy? Kinetic, kinetic, and energy potential. And guys, maybe rather than putting an and, why don't we put a plus? Because guys, what do we call the sum of kinetic and potential energy? We call that total internal energy. And that doesn't change. Just a second, Ronnie. So kinetic can become potential, potential can become kinetic, but the energy of the system doesn't change. Go ahead. No. Heat and sound are both ways to exchange energy, and that's not the same. Heat is not energy. Heat is an exchange of energy. The energy that heat, guys, this is deep. Heat is not energy. Heat is a way to exchange energy. What kind of energy? Kinetic energy. So hot is moving faster, cold is moving slower. And when energy transfers from hot to cold, we call that heat. That is a transfer of kinetic energy, but heat itself is not energy. It's a conduit to exchange energy. But again, maybe, but you've got kinetic energy. Your molecules are moving, right? But I would never know until I touch you. Now there's heat. But until there's transfer, there's no heat. There's just kinetic energy. Is that okay? That's important. That's not word games. That's important to understand that heat is transfer. Kinetic energy is the type of energy. Is that okay? Yeah. Yeah? That's a really interesting question, Sophia. So here, say that again so everyone hears it, and then let's talk. Yeah. Mm-hmm. Yeah. Is that heat? Here's the question. What's your system? Do you see? And let me think through that with you. So say that we're talking specifically about the heating of your blood. Okay? If you're calling your blood the system, then yes, that is an exchange of heat, because there's something in your body that's heating up your blood, and your body becomes the surroundings that's heating your blood. Now, what if you say the system is your whole body? Well, if your whole body is the system, then no, because your whole body can't heat itself. So then where does the heat come from? Well, then it's your food, and your food is part of this surround. So you can chase this mouse round and round in circles. But the idea is that if there's an exchange of heat, there has to be an interaction between system and surroundings. And if you're looking for that exchange, you've just got to carefully pick your system. Do you see how that works? Isn't that weird? Yes, and that's wait until we get into lab and we start mucking around with this and we start exchanging heat and you're like, oh my gosh, what's my system? Because if you pick your system wrong, you may be actually ignoring heat exchange. Yeah, we'll talk more. So guys, you good on that? Now let's do this. What about this idea of transferring? How does energy get transferred from system to surroundings? Two ways, guys. What are they? Work, which is W, and heat, which is Q. That's it. That's it. So here then is what this says. First law of thermo. Energy is never created or destroyed when internal energy interconverts or when the system exchanges energy with the surroundings. But guys, I'll bet you when you wrote down those first 6 or 7 words, your ears were itching a little bit. You're like, wait, this sounds familiar. Energy is never created or destroyed. What else do we know that's never created or destroyed? Matter. And what do we call that? The law of conservation of mass. Guys, the first law of thermodynamics can also be thought of as the law of conservation of energy. Now, guys, here's the idea, and we're not going to chase this down too far, but hear this. You guys learned last year that matter is always conserved. There is a finite amount of matter in the universe. And that matter never goes away. It is always, well, it's here, and we can exchange matter, but it always adds up. Matter that goes in has to equal matter that goes out. Well, guys, there's also a law of conservation of energy. There is a finite amount of energy in the universe. And if something's energy is going up, somebody else's energy is going down. The books always balance. Now, here's an interesting question. Where did all this matter and energy originally come from? My coffee cup, right? The Big Bang. That's the point. That all of the matter and energy in the universe came from that Big Bang. So we have a fixed amount of energy, we have a fixed amount of matter. It all came from the Big Bang, and what we got is what we got. You get the idea? But we're going to touch on this briefly, and then we're going to move on. Guys, with that said, please do not think that the amount of matter and the amount of energy in the universe is actually static. It is conserved, but it is not static. The reason is because energy can turn into matter, and matter can turn into energy. Says who? Einstein. Guys, E is equal to mc squared. What's E? What's m? They interconvert. Guys, energy can turn into matter, and matter can turn into energy. So the total sum of all the energy and matter actually is constant. And then we think about conserving energy and conserving matter. But in order to say that these things are truly conserved, you've got to understand that they can interconvert. An example is the bomb that we dropped on Hiroshima. Guys, when we dropped that bomb on Hiroshima, the universe became about 0.2 of a gram lighter. Because the current math is that 0.2 of a gram of the uranium in that bomb, 0.2 of a gram of uranium in that bomb got converted into energy. That's the energy that destroyed Hiroshima. Isn't that crazy? Less than a gram of uranium got converted. The numbers aren't clear. Some people's estimates range up to 10 grams, but still that's 10 paper clips, right? But guys, in that nuclear process, matter did get converted into energy. That's going on in the sun as well. And the numbers are staggering. Hundreds of millions of tons of hydrogen in our sun cease to exist every second. It's not that they're turning into something else, they're turning into energy. And guys, that is the energy that fuels our sun. Our sun is not burning. Our sun is literally taking hydrogen atoms and making them disappear. And they convert into energy, and that's the energy that we experience as sunlight. So guys, understand matter and energy can interconvert, but understand that the matter is conserved, law of conservation of mass, and energy is conserved, first law of thermo, but they can't interconvert in nuclear processes. Yeah? How do they make... We'll talk for a second. Did you hear the question? How does energy become matter? That's what the Big Bang was all about. So the thing that banged, we call the singularity. And it wasn't stuff. It was energy. And as that singularity exploded, the thing that exploded, weird thought, was energy. But as this thing expands, just like, have you ever felt the sides of a propane tank? When the propane comes out, the tank gets cold. When things expand, they cool. It's called thermal expansion. So when things expand, they cool. And as the universe, the Big Bang, as that thing expanded, it cooled. And as it cooled, energy literally condenses into matter. In the same way that dew condenses out of humidity, literally in the mind of a physicist, matter is just condensed energy. It's energy that is cooled down enough that it no longer exists as energy, it exists as matter. So quite literally, as that thing expanded and cooled, first protons, neutrons, and electrons started to condense, then they turned into atoms, and you remember the rest of the story. But that's literally how it happens, is through cooling. Yeah. Isn't that crazy? Isn't this neat? Do I dare say this? Can I say this? I'm going to say this. Go back and read Genesis, given what we just talked about. It's fascinating. It's really cool. Sorry, I shouldn't have said that, but okay. All right. So, guys, it was a suggestion. And I understand you can actually get the book of Genesis on this website, and you can download it for... No, I'm kidding. Sorry. Sorry. I couldn't resist. All right, so guys, let's now move forward and let's talk about this. Okay, so guys, now that we're wrapping our arms around this idea of energy, all of a sudden the only thing that's running through my head is the things that exist were made out of the things that did not exist. Sorry, I definitely shouldn't have said that. Okay, so guys, as we then move forward in this study of energy, we now need to start focusing our attention. So guys, when we study energy, we've got to talk about, and this is going to become a little bit of review, but guys, when we talk about energy, we've got to talk about all our sources of energy. Could you do something for me? Would you be willing to try not taking notes, because this is all review? Is that okay? Just try this. So guys, what do we call all the energy in a system? Internal energy. What is that made of? Kinetic and potential, right? So guys, when we talk about the energy in a system, can you remember that it's abbreviated E? It's actually an abbreviation that makes sense, right? And guys, it is literally the sum of all the kinetic and potential energy in a system. Now, with that said, guys, this is weird. Don't write this down, but you need to understand this. You can't directly measure energy. Isn't that strange? You can't go, gosh, I wonder how much energy this clipboard has, and shove an energyometer into it and measure it. We can measure temperature, and we can measure velocity. But guys, we can't directly measure energy. Here's where we need to talk. Do you remember in chapter 5 where it talked about state functions? Say yes. No. If you don't remember state functions, guys, state functions are a really, really big idea. They're in chapter 5. State functions are a really, really big idea. In college, you will dwell on them extensively. What I found is this. trying to teach you about state functions is unnecessary. You can understand the things that we're talking about without understanding state functions. And I'll be honest with you, I have about a 50% success rate trying to get people to understand state functions. So right now, we should talk about state functions. Takes about half an hour. Finally, everybody goes, yes, I get state functions. You go to do the homework, only 50% of you do, and then we're all just all over the place. So what I've learned is if we don't talk about these as being state functions, it clears up the confusion and it doesn't take from the concepts. So guys, we just said this, that when we study energy, we can't talk about its empirical values. That means we can't directly measure it. We can't stick an energy-ometer in something. Why? Because because it is a state function. Don't worry about it. Let's just talk about the solution. Guys, when we talk about energy, we do not talk about, we don't measure energy. What we do is we measure energy change. And guys, energy change, like any other change, is final minus initial. And then guys, from there we can simply say this. Ready? If the final energy is greater than the initial energy, then the energy change is positive. Guys, think about that. If the final energy is greater than the initial energy, then the energy change is positive. Does that make sense? Imagine that I'm the system, and I start with 100 joules of energy, and then something happens to me, and now I have 200 joules of energy. Did my energy go up or down? Up. That's right. But 200 minus 100 gives you a positive number. And then, guys, conversely, if final is smaller than initial, then energy went down. But, guys, here's the question. Let me make it a statement. This begs that your frame of reference is in the system. Does that make sense? So when we say that energy is going up or energy is going down, if final is greater than initial, the energy went up for the system. What about the surroundings? It went down by the same amount. So guys, fundamentally what we're saying is this, that when we talk about energy, we're going to talk about change. When we talk about change, if the final's greater, it went up. If the initial was greater, it went down. Is that okay? Okay, so guys, let's do this then. Let's take this idea and let's bring this to our picture. Go back up to your picture. Did y'all draw? If you drew the picture. So guys, here's what we know. Kinetic can become potential and vice versa, and that doesn't change E. How do we change E? That would be the amount of work and the amount of heat. But guys, the change in energy then, and this is worth writing down, the change in energy then for the system is equal to the amount of work plus the amount of heat. Does that make sense? If the only way to get energy in and out of a system is work and heat, then if you can measure work and if you can measure heat, you can then figure out how much energy changes. Now, guys, let's go back to our picture. Here's our system. Once again, what does that make everything else? Surroundings. And guys, we've said this. We've said that energy can get in and out of the system. But if you drew the picture, break up the arrows. Because there's two ways to get energy in and out of a system, work and heat. But now, guys, we've got to talk about the directions. So let's do this. First thing we need to do is we need to figure out, we're going to talk about direction and we're going to talk about sign. This requires a frame of reference. So guys, ready? Where are you? Are you in the surroundings or are you in the system? In chemistry, you're in the system. In physics, you're in the surroundings. But guys, if you are in the system, now let's lend signs to these things. So guys, let's say that the left-hand side, let me zoom in so you can see this. So guys, let's say that the left-hand side is work. Think about this logically, guys, watch. If the system is doing work on the surroundings, is energy going up or down? Let's do it again. If the system is doing work on the surroundings, Is energy going up or down? Well, the question is, whose energy? But where are we? In the system. So let's do it again. If the system is doing work on the surroundings, is energy going up or down from our reference? It's going down. Guys, it's going down because we are in the system. Now, guys, what if the surroundings do work on the system? What's happening to energy? Well, now it's going up because the system is gaining energy and we're always in the system. Do you see why reference and position is important? Because, guys, in physics, the signs would be different. In physics, we would go, no, work is positive because work's coming towards me. But our frame of reference is in the system, and that means if work is going out, energy is going down. Now, what about here? What if heat is going in? Is energy going up or down? Up, because we're in the system. What if heat is going out? Well, then energy is going down because that's in the energy is going to the surroundings, and we're in the system. Yeah.
So, simplify a little bit. So if you're doing like an exothermic reaction.
Ooh, guess where we're going next? That's actually next time. Go ahead.
So it's like an exothermic reaction.
Mm-hmm.
We would, our point of reference is from the reaction, right?
Correct. So let's say that very clearly. In this class, your system is the atoms that are reacting. Either as a reactant or a product, law of conservation of mass, right? What goes in comes out. Your frame of reference is always the atoms that are involved in the reaction. So now keep going. Negative. And so what you're going to find out is that heat is negative for exothermic reactions. That's going to be a slide on next day's stuff. Yeah. Although at that point, we're not going to call it heat. We're going to call it enthalpy, and that's what we're doing for the rest of the day. You're not going to like it because actually, well, we'll talk. So, yeah, you'll see. Guys, you good on these ideas? You're good? Okay. So, gang, in the madness that has become my life, as every time I open up my email inbox, I find out I've got 17 more kids quarantined. I have not yet had the chance to look over your Chapter 5 summaries. So I'm just going to ask this as a question rather than say, hey, I looked over your summaries and guess what I saw? So I'll ask it as a question. Guys, when you did the 4-quadrant thing, you're like, oh crap, there's supposed to be 4 quadrants. You had concepts and equations. No, you had concepts, equations and concepts, diagrams, and then questions. And guys, the questions section is where you get to write down the I don't know what this means thoughts, right? Guys, did any of you include enthalpy in that section? Beautiful. I am about to earn my salary for the day. Because guys, for the rest of the day today, what we're going to do is we're going to talk about enthalpy. You can thank me for this later. So guys, setting the stage for enthalpy. In order to set the stage for enthalpy, there's a term that we need to define. But this term is also confused with another term that we already talked about. So let's go back and clarify. Guys, what we said is that whenever we do thermochemistry, they will always be closed systems. What does that mean? Closed. Energy can get in and out, not matter, right? So law of conservation of mass holds true. No matter is lost, right? Okay. Guys, with that as a foundation, in order to understand enthalpy, there's another container you need to know about. These are what are called open containers. So guys, in order for us to study enthalpy, and I don't expect you to understand this. I just need to get this word, this 2 words in your hands, in your head, in your hands. So guys, when we talk about enthalpy, the bridge to understanding the concept is a thing called an open container. Now guys, on the AP test, you are welcome to use the term open container. That is a shared way of thinking about this. When you get to college, you'll probably find your professors call these things constant pressure containers. We'll talk more about that in a minute because that's really what they are. But guys, if you would like to use the more familiar reference, you're more than fine to call these constant pressure containers. So guys, let me define for you then a constant pressure or a open container. So guys, an open container is a hypothetical container which offers no resistance to expansion or contraction. Once again, an open container is a container that offers no resistance to expansion or contraction. So guys, write it down, then we'll talk about what it means. And then guys, we'll talk about why this is important. So guys, imagine this. I'd grab one, but I don't think it's necessary. You guys have all blown up a balloon, right? Yeah, sure. So you grab the balloon, maybe you stretch it first, and then you start to blow up the balloon, which I'm not even going to mimic because I don't want to spit all over you. But you start to blow up the balloon, right? Here's my question. Guys, don't miss this. Ronnie, be careful. When you blow up a balloon, are you doing work? Remember the two things that need to be there. Is there movement? Yeah, movement of molecules, movement of balloon material. Is there resistance? What is the resistance? The elasticity of the balloon. That's why we stretch it first, because then we have to do less work. Because doing this work stretches the balloon, which then means when we do this work, we have to do less work because we've already loosened it up, right? But guys, are you in agreement that when you blow up a balloon, you are doing work because there's movement against resistance? Is that okay? Now, imagine a magical balloon. Huh? Imagine a magical balloon that as you blow it up, it magically just gets out of the way and expands exactly enough to contain the amount of air you're putting in without offering any resistance. Does such a balloon exist? Heavens no. But guys, that is the mental picture of an open container. It is a hypothetical container that offers no resistance to expansion or contraction. Now guys, why is that concept important? If you were to blow up this magical open container balloon, are you now doing work? Why not? There's no resistance. Does that make sense? Because that's important. Guys, the therefore then is this. No work can be exchanged. If there's no resistance, there's no work. Because work requires movement against resistance. But guys, this is where things get really interesting. You ready? Let's go back and review what we already know. What are the two ways we can get energy in and out of a system? Work and heat. Guys, that's it. The only way to get energy in and out of a system is work or heat. Now, guys, do this with me. Imagine that your system is a chemical reaction. Yeah? Here's the question. how do chemical reactions, coming to your thought earlier, Matt, how do chemical reactions release energy? Well, the only way anything can release energy, work and heat. So guys, how do chemical reactions release heat? Well, as a chemical reaction happens, the particles vibrate faster. They smash into the particles in the surroundings. Those particles speed up, and we're releasing energy in the form of heat. Does that make sense? Here's the interesting question. How do chemical reactions do work? Chemical reactions can't lift shovels and scoop dirt, right? How do chemical reactions do work? Ready? Expansion. Think about it. Gasoline, right? That magic chemical that we use to do work to move our cars. But how does gasoline move your car? Well, guys, gasoline, when you put it in your car, goes into the engine. And in the engine, that gasoline goes through a chemical reaction with oxygen in a cylinder. And when that happens, the gasoline explodes. And when it explodes, it expands. And when it expands, it pushes on a piston that spins a rod, that spins another rod, that makes your wheels move. But guys, that's literally how chemical reactions do work. They expand. But guys, what about this? What if we do all of our chemical reactions in open containers? Can they expand? Absolutely. But why are they not doing work? Because there's no resistance. And guys, if that's the case, if we do our chemical reactions in open containers, chemical reactions can no longer do work. They can expand, there's just nothing to push on. And when that happens, when work is gone, guys, now we're only left with one avenue. If we can get rid of work, if reactions can't do work because there's no resistance, then the only way chemical reactions can lose energy is through this guy, which is what? Heat. But guys, heat, in the absence of work, gets a new name. Enthalpy. That's it. Enthalpy is heat in the absence of the ability to do work. Enthalpy is heat in the absence of the ability to do work. So guys, let me pull that up for you. Uh-oh. My screen just totally freaked out. So guys, it's literally this simple. Enthalpy is heat exchanged in the absence of work. Now you're thinking to yourself, wait, this is stupid. If open containers really don't exist, then why do we even talk about enthalpy? Because that can't be the case. Well, guys, imagine this. Imagine that you detonate a bomb. Does that bomb do work? Not until it runs into something. If you were to do, because that the gases from, and that's all bombs do is make gases that move out really fast, right? But guys, if you detonate a bomb up in our upper atmosphere where there's nothing in the way, there's barely any air up there. If you detonate a bomb all the way up there, that thing just expands forever and it never runs into anything, so there's no resistance, so there's no work, right? Well, guys, imagine that instead of a bomb, imagine that you are doing a reaction on your lab bench. If that thing does try to expand, it's just going to expand out into the room. And there's not a lot of resistance in the room. So, guys, understand that while these open containers are fictitious, they're very good approximations of the place where most chemical reactions take place, because literally the containers are open. And if these things are going to expand, there's not a lot of resistance against expansion, unless we put a lid on it and then we made a bomb, right? But guys, the idea is that a lot of times chemical reactions actually can't do work for real because there's nothing to push on. Yeah. Yeah. Absolutely. Yeah, so, and that's the idea, that this is close enough to real that many times it works. Now understand, and we're going to talk more about this in the next chapter, that this whole idea of enthalpy actually was created by a guy who was trying to design more efficient steam engines. He was frustrated because he knew how much energy was going in the form of coal, and he knew how much energy was coming out in the form of motion. And he realized the books did not balance. What was going in and what was coming out was not the same, and it wasn't because of friction. And so then all of a sudden this expansion does become important. If you want to read more about that, there's a thing in our book that talks about what's called PV work. It's one of those little pull-out sections. I think it's in chapter 5 and not 19. There's a little bit about it there. But anyway. So guys, are you okay with this idea of enthalpy? Okay. So, gang, let's then take this and let's bring it full circle. You're not going to like this. So, where's my clicker? There it is. So, guys, when we talk about enthalpy, we need an abbreviation, right? You want to guess what it is? You're not going to like it. Guys, the abbreviation is actually H. So, ready? Heat is abbreviated Q, and enthalpy is abbreviated H. Because we're not in charge, right? At least it has an H in it. It's not even second or third. Well, third. I know. Although, guys, the reason that they abbreviate heat Q is because they originally thought of heat in packed quantum of, anyway, it's a long story. So guys, now we can talk about not changes in energy, but changes in heat. And actually, it turns out, Matthew, we're going to talk about this kind of now. So what if the final enthalpy is higher than the initial enthalpy? Well, guys, that would be, the other way around. No, what if final is greater than initial? Well, guys, we call that endothermic. So positive delta H's are endothermic. These take in. We will come back to this next time, too. But then, guys, negative delta H's give off heat because energy is coming out in the form of heat. I don't know where you're making the connection with rockets. And I mean, they go ahead. Yeah. I think I know what you're saying. So the idea is that, when if you set off a bomb in outer space, it expands, but there's nothing to push on, so no work is being done. If you're then thinking about rockets, this is really counterintuitive because rockets aren't pushing on anything. That's not why rockets propel things. It's not like a rocket goes and it shoots gas out the bottom and that pushes the rocket. That's not how that works. If it was, rockets wouldn't work in space because in space there's nothing to push on. So this is where you got to start thinking about Newton's law of motion. And for every action, there's an equal and opposite reaction. So literally, the gas coming out of the tail of the rocket is the action. The reaction is an equal force in the other direction, pushing the rocket. But it's not because the gases are pushing on something. It's literally because, is that the second law of motion? Equal and opposite reaction? It's not because it's pushing. So at that level, they're not related. All right, guys, so let me show you where we're headed with this, and we're going to wrap up the day. So we now need to, let me go back. We now need to take this idea of gaining and losing enthalpy, which is heat in the absence of work. Oh, sorry. And guys, we talk about this as final minus initial. All change is final minus initial. But now we're going to link this to chemical reactions. So guys, watch. Where do chemical reactions finally end up? Products. Where do they start? Reactants. So let's substitute. Yeah? This is the change in enthalpy equation simply applied to reactions. And guys, this leads us to an interesting thing that are called thermochemical equations. So we are really, really used to looking at reactions and going reactants and products. But now, guys, check this out. How about reactants and products and then a delta H value? So hydrogen synthesis reaction reacts with oxygen to make water. Yeah, that's true. But guess what? It also exchanges heat in the absence of work, which we call enthalpy. So the enthalpy change for that reaction is negative 483.6 kilojoules. Given how light hydrogen and oxygen are, it's pretty good. It would cook a marshmallow. So guys, let me ask you some questions. If you were standing next to this reaction, would it feel warm or cold? Warm. How do we know? Because that number's negative. What does that mean? Well, that means our system, which are the hydrogen and oxygen atoms, are giving away energy. Negative delta H. They're giving away energy. Where does the energy go? Into the surroundings. So if we were standing next to this, we would enjoy that warmth, that heat, because energy is going out. And the products. So as reactants turn into products, mass is conserved, and during that conversion process, energy comes out. Okay. So guys, let me ask you some questions. How much hydrogen has to burn in order to give off that much energy? How much hydrogen has to burn? Let me grab my pen. So how much hydrogen needs to burn in order to give off this much energy? Answer? 2 moles. How much oxygen needs to burn to get out that much energy? 1 mole. Now, what if we did 4 moles of hydrogen? What would happen if we did 4 moles? We would get more heat. How much more heat? Twice. It would be 960 or whatever. So guys, these are properties that scale with amount. So if this is 2, it's that. If it's 4, it's that. Now guys, what about this? What if instead of making water, what if we took water and broke it apart and made it into hydrogen and oxygen? If we reverse the reaction, the question is this. If we're going to turn water into hydrogen and oxygen, does energy still come out? No, now it goes in. So if energy comes out as water is formed, energy has to go in as water is broken down. How much? This much. The sign changes. So it takes this much energy to break down 2 moles of water. Because why is that true? Why does energy have to go in to break up the water? Where does the energy go? into the breaking of bonds. Guys, anytime bonds are broken, that is endothermic. Regardless of what your biology teachers told you about ATP turning into ADP, and when the bonds break, energy comes out, that's a load of crap. That is not true at all. That is horrible science. They don't want to teach it to you. But when ADP, triphosphate, turns into ADP, diphosphate, when that bond breaks, energy goes in. That does not release energy. Anyway, guys, this is where we're going to pick up next time. Guys, this is your homework. You already saw it. Let me bring it back. Here's your homework. This is just a rehashing of everything we just talked about. There, guys, is your homework. We will grade these on Tuesday. And then, guys, on Tuesday, we're going to answer a really interesting question. How do we know that 480 kilojoules of energy comes out when oxygen turns into hydrogen? We're actually going to talk about what does the lab apparatus look like where these numbers come from. It's great stuff. So, guys, let's take a break. Michaeli, see you. And we'll come back in a few minutes.